Hello everyone. Today we will be doing the second experiment using the double and toolbox of MathWorks. So before going to the second experiment, I would like to review the path loss model what we discussed in the last video. There was some recording glitch because of which the particular slide was on mute. So to determine the achievable range between the transmitter and receiver, a path loss model is generally required. The path loss model captures a power fall off relative to distance. The free space path loss model is the first equation here. This is the free space path loss model, which solely depends upon the distance and the operating wavelength of the frequency. This does not accurate for general environments. There are various path loss models. Empirical path loss models are based on extensive measurements. Empirical models widely used to study cellular and Wi-Fi performance via simulation. The standard body for cellular, that is 3GPP, and the standard body for Wi-Fi, IEEE 802.11, develop classes of propagation models such as indoor, outdoor high speed, outdoor low speed, etc., which are used to evaluate different technology proposals to the standard. Simulation packages often integrate these models into their software for ease of simulations. In IEEE 802.11n and 802.11 AC models, the path loss model is free space model up to a breakpoint distance, and then it has a 3.5 path loss exponent. So as we can see here, less than the breakpoint, it's a free space loss model, and after breakpoint distance, the exponent is eta, and it is 3.5. So the third equation gives the path loss in decibel. So same thing is captured in this table. You have different channel model B and channel model D. The breakpoint distance for model B is 5 meters and for D it is 10 meters. The slope before breakpoint distance is 2 and slope after the breakpoint distance is 3.5. So coming back to our current experiment, that is a channel frequency response for indoor channel models. So the learning objectives is to create a single user high efficiency format configuration object and initiate the transmit parameters for HE single user format of IEEE 802.11ax standard. So I call here as high efficiency because 802.11ax or Wi-Fi 6 is also known as high efficiency WLAN. Next, we configure the task group AX. TGAX here refers to the task group AX channel of 20 megahertz bandwidth. We obtain the channel frequency response, that is magnitude of H of high, using HELTF field of the packet preamble. This is a training field which is used to estimate the channel. And we obtain the statistical distribution of the channel gain and also compare the channel gain, that is magnitude of HI squared, for different indoor channel models. So as we have seen in the previous video, there are 6 channel indoor channel models, out of which these 3 channel models are widely used for proposals. So this is a residential, indoor typical residential. This is indoor typical office, and this is indoor large office or warehouse. When you compare these, the channel model he has highest RMS delay spread and the maximum delay which is in nanoseconds, and also the breakpoint distance is higher and it's 18 tap filter. So we will come back to this table after going to the program and the simulation results and try to understand in a much better way. So now we are good to go to the program. So now, so this is a program to find the channel frequency response using the HELTF field of the packet preamble. So here I've created a WLAN HESU configuration object for HESU format for 11ax standard. The bandwidth, the operation bandwidth used 20 megahertz. The PSTU data length is 100 bytes. Here I'm generating a random bit pattern using randi, creating a PSTU and passing it as an input parameter to the WLAN waveform generator. This WLAN waveform generator is going to give me a transmit waveform, which is of size ns cross nt, where ns is the number of complex symbols and nt is the number of transmitting antennas. Since I've considered CISO, nt is 1. So tx waveform length is 3600 complex samples. So WLAN waveform generator, what actually does is it takes in the random bits These bits are mapped to the constellation symbols using the constellation mapper. And this complex symbols is again fed to the IFFT block, and you get the complex samples. So here within this, the bits are converted to complex symbols, constellation symbols, and then IFFT is also done in order to obtain the complex samples. So this is a TX waveform. So we have 3600 complex samples. So here I'm trying to just see what is the transmit power associated with the TX waveform by taking mean of TX waveform and its conjugate. So this index, the double land field indices gives the different index points for the different fields within the packet. So if I see what is in here, LSTF, the first 160 samples in the transmit waveform corresponds to LSTF. 161 to 320 is LLTF, and we saw there were 3600 samples. So the HE data corresponds to 1041 to 3600 samples. The HE LTF here is about 320 samples, that is starting from 721 to 1040. So next what I'm doing, I'm using these index points referring to the HELTF, trying to extract this HELTF from the TX waveform and store it in HELTF transmitted. This is what HELTF transmitted. This is HELTF constellation symbols, and IFFT is applied on that. So we have complex constellation complex samples. That is for the constellation symbols. After IFFT, what we have is 320 complex samples. So we will use it later. I'll come back to this again. So this, just keep this in mind. So next we configure a TGX channel, which is of 20 megahertz. The distance is set to 12 meters and the TGX sample rate is 100 megahertz. So here for bandwidth less than 40 megahertz, the tap spacing is 10 nanoseconds. So the sample rate is set to 1 over 10 nano, that is 10 power 8, 100 megahertz. Again, path gains, in order to obtain the path gains, I'm setting the output port to true, and the channel delay profile is model D. So here I'm passing the impulse input to the TGX channel. So what is the channel we have created? It is TGAX. So I can use this object and give any input signal to it. You will get the output of the particular channel, TGX channel. So input here I have created 100 zeros, and the first sample is set to 1. So this is like an impulse input. So I'm given an impulse input to the TGX channel, and this is the impulse output. So it is nothing but the impulse response. I am calling it as impulse IMPR1. So this I'll compare with the impulse response, which is obtained using the path gains. This we have seen last video. There's a TX waveform. If you pass through the TX waveform, you get path gains as well as TJX output. Using these path gains, you can find the impulse response. First, we obtain the non-zero tap index. Then we get the NH, that is the length of the impulse response. Then obtain the impulse response. So here I'm comparing the IMPR, which is obtained using the path gains, and the IMPR1, which is obtained simply passing the impulse input to the TGX channel, and comparing the samples. This is the first figure. So y-axis is simply the samples. So you can see there is a perfect overlap between the channel impulse response, which is computed from the path gains, and CIR, which is computed from the impulse input. These are red in color. They're all zeros because I think the length of the impulse input what I chose was 100. Yeah, 100. First sample being equal to 1. So we have 100 samples. The remaining samples is 0. And this is the impulse response, which is obtained from path gains and impulse input. There is a perfect overlap. The second figure is as usual, which is obtained channel impulse response obtained from the path gains. And this I have sketched with respect to the time domain in x-axis. So we have, using the TGX sample rate. So this x-axis corresponds to the tap spacing. If you see the tap spacing between these two, it is first is 0, second is 1 exponential 8, that is 10 nanoseconds. This is 2 exponential 8, so this is 10 nanoseconds. So this is a channel impulse response, 18 tap filter. Channel model D is 18 tap filter. So now I had obtained this HELTF, extracted this HELTF from TX waveform, right? What is this HELTF? This HELTF is nothing but the complex samples which is obtained after applying IFFT. So now what I do in order to obtain that HELTF pilot symbols, I do HET modulate. Yeah, I use WLAN HET modulate. So HELTF transmitted is after I am applying IFFT. So what will XK have? It will do FFT. So you get back the constellation symbols XK. So if you see here, the constellation symbols XK is BPSK signal. So the HELTF field is actually BPSK modulated because it is robust. So these are the pilot symbols and this is standard defined. Here I'm computing what is the power associated with it, and also I'm displaying the real part of it. Since it is BPSK, anyhow the imaginary part is 0. So if you see the real part, it is either +1 or -1, and this is defined by the standard. This is the sequence of HELTF, that's the 320 values. So it is BPSK modulated. This is the transmitted symbol and it is defined by the standard. So I have XK now. So now in order to obtain the channel frequency response, I am writing another function where I send this TJX, TX waveform, CFGSU and also XK. So we'll go to this particular function. So what this function do? This function is going to take these input parameters. First, I'm initiating L is equal to 5000. That is the number of channel realization. HK at, it's an open array, which I'm going to compute. So for 5000 channel realizations, every time I'm resetting the channel. So in order to create the new independent channel realization. So now I'm going to pass the TX waveform through the TJX channel. I get the TGX output and the path gains. So this TGX output is nothing but the output from the channel, the receiver waveform. So now again I'll make use of this in IND, that is in order to get the index values for different fields. From the receiver waveform, I'm going to extract the HELTF portion. So this RX HELTF is the HELTF waveform. Again, it's a set of complex samples, but it is at the receiver end, that is after passing through the channel. So the size of it would be 320 cross 1. So what I'm going to do, again, I make use of HET modulate in order to obtain the HELTF demodulated data. The difference is earlier in this year also I had used the same function, but I was trying to obtain XK, that is the transmitted HELTF constellation symbols using HET demodulate. Here, since it is passed through the receiver, this will have the effect of the channel in it. So this YK is again this would have done FFT on this RX HELTF and I get YK. Because there is a fading effect, this YK will not be equal to XK. So now for all subcarriers, this YK, the size of this would be 242 because HELTF would occupy 242 subcarriers. Okay, though in 20 megahertz we have 256 subcarriers. The occupied subcarriers is 242. You have the guard interval to the right and to the left. I think that is also, yeah, here. So this RU size is 1. It occupied 242 subcarriers. So here this point is 122. The left here it is minus 122. So here up to, here you have around 6. Here also you have around 5 guard subcarriers, and in between there are 3 subcarriers. So 6 plus 5 plus 1, around 6 plus 5 plus 3. 14 subcarriers are unused. So 256 minus 14, 242 are the occupied subcarriers. So the length of this HELTF is 242. So now what you do, for each of these subcarrier, I'm simply taking the ratio YK divided by XK. YK is which you have received at the receiver, XK which is transmitted. One point you should note that I have not added any AWG in here. This is simply only fading effect is there. This is just because I just wanted to sketch the channel frequency response using the HELTF field. So there was no need to, so I did not add any AWGN. So this is one such method of obtaining channel frequency response, and I wanted to characterize, statistically characterize, like how does it look, and I was more interested on the statistical characterization of the channel frequency response. So I hope this is clear. So now you have the estimated HK, that is the channel frequency response at kth subcarrier. So this I'm going to collect. So this I get for one particular realization, I'll have 242 cross 1. So I'm going to repeat this for 5,000 realizations, and I'm going to collect all these. So this HK hat has now 242 cross L, that is 242 cross 5,000. There is the dimension of this HK hat. Then I'm going to calculate PG, that is HK absolute squared. This is again 242 cross L. So for every column of PJ, what do you have? You have HK squared for all the subcarriers, that is K equal to 1 to 242, which corresponds to one channel realization. And if you go to row wise, what happens? Row wise is again a random variable for a particular K. If you access HPG row wise, you will get to see how does that random variable vary. Okay. So both CFR and PG I'm sending back as a output parameters. So here you get CFR and PG. So now here I'm going to sketch the 5 realizations of, and also the average of 5,000 channel realization. Sorry, I think I have sketched only 3. So randomly I have just picked a 90th column, and I've sketched here the channel frequency response HI first. So here if you see, yeah, this is the channel frequency response of which is sketched for 242 subcarriers for model D. Then I'm going to sketch, yeah, plot for 3 channel realization. This is magnitude HK squared because PG was absolute value squared. Absolute value squared. So just pick some numbers at 10. I've just randomly picked 10th column, 40th column, 90th column. You have 5,000 such columns. You can pick any of those columns. Each column will give you different channel realization. So you will have h of k or h of magnitude hk squared plotted for all 242 occupied subcarriers. So this is the plot. And also I think have sketched the average of all those 5,000 realizations, which is sketched in this. So if you see, the average value is around 1. It's almost varying about 1. And this 3 different channel realization, this is magnitude hk squared. So here I have sketched the average value of 5,000 realization. So now the channel frequency response, what I had, again, that was also a matrix of 242 cross 5,000. So if you go to any row, any again random row, here I have chosen 72 row. Here what you will see, you will have capital H72. You have 5,000 such random variables. You have 5,000 data points. So using this, you can obtain the statistical characterization. You can obtain the histogram, and also you can see which is the best fit for this particular random variable. So this is collected in this row vectors. This you have 5,000 random variables. Normalization is set to PDF. Then I'm going to use the fit distribution function and see whether it fits to Rayleigh. And I'm going to plot the Rayleigh PDF. So yeah, this is the histogram of 5,000 channel realizations. Subcarrier index is chosen at random 72. You can choose anything between 1 to 242. So it is fitting Rayleigh distribution. Then I'm doing the same thing, but this is for magnitude HK squared. Rest all is the same, but the input is row vector, and row vector is obtained from PG. That is the magnitude HK squared. Again, I have chosen 72, but you can choose any, you are free to choose any value between 1 to 242. If I sketch here, the distribution is exponentially exponential. Magnitude 872 squared is exponential distribution. The magnitude 872 is Rayleigh distributed. So here, whatever I have sketched, this is for channel model D. You can, what you can do, you can change this channel model D to model B, model E, and see what is a change. And also you can think intuitively or reason out why is that characteristic function is changing with the different indoor channel models. So coming back to the slide, yeah, this I've done. So whatever we saw was this for channel model D. If you simply change the channel model to model B or model E, you will get to see the response like this. From these, it's very clear like the channel model B is somewhat slow. The variation here is slower. This is more, and here it is even more. This is because if you go here, the RMS delay spread is highest. It's increasing from model B to model D and from model D to model E. The model E has a highest delay spread. And we know like has a delay spread TD increases, what happens. So if the delay spread is lesser than the symbol duration TS, it means the bandwidth is much less than the coherence bandwidth of the channel. So the coherence bandwidth of the channel, say here it is the variation, maybe somewhere here. The flat portion is the coherence bandwidth. So if the coherence bandwidth of the channel is larger when compared to the signal bandwidth, then all the frequency components of the signal will experience the same magnitude of fading and the channel is said to be frequency flat. But as the TD increases, what happens? As TD increases, the coherence bandwidth decreases. So the channel becomes more and more frequency selective. So here, compared to D, uh, compared to B, D has more delay spread. Compared to, if you compare these two model, he has more delay spread. So same thing is observed here. Since delay is increasing, the coherence bandwidth is decreasing. The channel is becoming more and more frequency selective. The variations are larger here. And this based on there is the magnitude squared is following exponential distribution. So to summarize, each subcarrier is modeled as a circularly symmetric complex Gaussian random variable with zero mean. The magnitude of the channel frequency response follows the relay PDF and the magnitude squared follows exponential distribution. The channel model here has a longer delay spread other than the two channel models and therefore is more frequency selective. Thank you.